In this video, we're going to look at the shapes that these molecules that we've been drawing dot and cross diagrams actually take up in three-dimensional space. So what's important to think about when you're talking about shape is that we aren't occupying two-dimensional space like on a page. We're going to take up as much space as we can in 3 dimensions. So things are going to get as far apart from each other as possible, and by things we're actually talking about pairs of electrons, because the pairs of electrons that sit in those orbitals, remember 2 electrons in an orbital, the pairs of electrons in those orbitals, they want to be as spread out as possible around that central atom. And so the shape that we're going to look at is primarily determined by how many pairs of electrons there are around that central atom, and then the types of pairs of electrons. So are those pairs of electrons in bonds? So they're kind of a little bit further out from the central atom because they're shared between 2 atoms, or are they lone pairs more compact in on top of the central atom? Those 2 types of pairs will have a slightly different effect on the shape. Okay, so all these pairs of electrons are going to repel each other to get as far apart as possible, because repulsion is minimized if they're as far apart as possible. And then lone pairs are going to repel slightly more than bonded pairs because they're closer to the central atom, they're more compact. So the theory explains to us that if we have a lone pair and it's next to another lone pair, that lone pair repulsion is going to be the strongest because they repel the most. And that's going to be greater than if we have a lone pair repelling a bond pair. Which is greater than if we have 2 bond pairs repelling each other. Once we look at these pairs and we decide how many there are of each type, we're going to try to minimize any repulsions we can by spreading them out in 3-dimensional space as far apart as possible. If we have a lone pair on our molecule, central atom of our molecule, it is actually going to change the bond angle by 2.5 degrees for every lone pair. And this is in comparison to the shape that is all bond pairs. This will make more sense as we go through. When we're drawing in 3 dimensions, we have 3 types of ways to draw a bond. If the bond is on the paper, we will draw it as a straight line. So if it's in the plane of the paper, if it's coming out of the paper, we want to draw a wedge. That wedge shows that that bond is coming out towards the reader, out of the paper. If the bond is going backwards into the paper, we're going to draw a dashed line, and that dashed line is kind of decreasing like an opposite wedge. But in an exam, if yours isn't actually getting much smaller, it will still be marked correct. Okay, so how do we find out the number of pairs of electrons around the central atom without drawing the dot and cross diagram? Because we might want to save ourselves time. At A-level, we're not going to be asked for the dot and cross diagram. So what we want to do is be able to work out how many dots and crosses there would be around that central atom without drawing it out. So we start with the group number of the central atom, because remember the central atom will have, if it's in group 5, 5 electrons in its outer shell. If it's in group 3, 3 electrons in its outer shell. For every bond that we form to another atom, we're going to add an electron, because that atom is going to form a covalent bond, with the other atom, the central atom. It brings 1 electron to the bond, so we're bringing 1 more electron to the central atom. And then we're going to account for any charge that's on our molecule or our ion. And if they're negative, we add, because you've added an electron. If they're positive charges, we subtract, because we've removed electrons. That's going to give us the total number of electrons. If we divide by 2, we'll find how many pairs. And if we then look at those pairs, we can look at the formula to decide how many are lone pairs and bond pairs. So if I just give you an example from a dot and cross diagram we just drew, if we have a lone pair on our molecule, central atom of our molecule, it is actually going to change the bond angle by 2.5 degrees for every lone pair. And if we then look at the formula to decide how many are lone pairs and bond pairs. So if I just give you an example from a dot and cross diagram we just drew, in a previous video, if we think about the ammonia molecule like this, the central atom is nitrogen, so we would start with the group number 5. There are 3 hydrogens attached, so we'd add 3 electrons. That's for the 3 dots that we're bringing by adding 3 hydrogens. There is no charge, so we don't do anything for charge. Add that up, we get 8 electrons. That's 4 pairs. If we look at the dot and cross diagram, we can see there are 4 pairs of electrons around the central atom. How many of those are bond pairs? Well, we look back at how many atoms joined on, so that would be 3 bond pairs, which means that if there's 4 pairs altogether, there must be 1 lone pair. And if we look at our dot and cross diagram, we can see there are 3 bond pairs and 1 lone pair. So let's have a go. We're going to build up our different shapes. We're going to start with shapes of molecules where there are 2 pairs of electrons around the central atom. We're going to start with BeCl2. So the central atom is the thing that there's only 1 of, but beryllium is in group 2, so we write 2. There are 2 chlorines attached, so 2 bonds are formed. There is no charge on this, so we write 0 here. And then we add it up. So the total is 4 electrons. So how many pairs is that? That's 2 pairs. 2 2s are 4. So if we look at it, if there are only 2 bonds, then there must be 2 bond pairs. And if there are only 2 pairs altogether, there can't be any lone pairs. So what is this shape? It's a Be in the middle. It's got a Cl on the left and a Cl on the right. This is the shape that minimises the repulsion as much as possible, puts those 2 pairs of electrons that are in these sticks as far apart as possible. That is called linear because it's forming the shape of a line, and we can see straight away that the bond angle is 180 degrees. How would we explain to the examiner this shape? So it would be give the shape and explain. So what did we do? We came to the conclusion that there were 2 pairs of electrons around the beryllium atom. Electron pairs repel to get as far apart as possible. This minimises the repulsion. So our bond angle is the angle between the bonds here, 180 degrees. And that is minimising the repulsion. So what happens if we then go to 3 pairs of electrons around our central atom? So an example of a molecule like this would be BF3. So boron is in group 3. We can see that there's 3 Fs, so there must be 3 bonds formed. There is no charge on it. If we add up those total, that's 6 electrons. 3 add 3 is 6. 6 is 3 pairs. So because there were 3 bonds, then there must be 3 bond pairs. And because there are 3 bond pairs and only 3 pairs in total, there must be 0 lone pairs. Now, if you've got 3 things and they're trying to spread out as far apart as possible, they do still stay in a 2-dimensional arrangement, and they look like a triangle. And we can say that this angle, 360 round the hole, divided by 3 is 120. That shape is called trigonal because it's like a triangle, planar because it's flat in 2 dimensions on this page with a 120 degree bond angle. So there are 3 pairs of electrons around the boron atom. Electron pairs repel to get as far apart as possible. Got another example here. So Sn is in group 4. It's got 2 chlorines attached to it. There is no charge. This adds up to 6 electrons or 3 pairs. We are still doing shapes with 3 pairs of electrons here. But if we look at it and we look at how many bonds we've got only got 2 bonds. So 2 bond pairs. Now, how do we get to 3 if we've only got 2 bond pairs? We must have 1 lone pair. So we've got 2 bond pairs and 1 lone pair. So we still have 3 pairs of electrons. That's what's important. Put the SN in the middle. And what I would suggest in an exam that you do is you sketch out the 3-pair shape in pencil, which is to repel each other 120 degrees. But actually one of these doesn't have a Cl on the end of it. One of them is a lone pair. So we rub out the 3rd bond and we change it to be a lone pair. Okay, so we've got this, it's still got this trigonal shape, but we've got 1 lone pair and 2 bond pairs. So we don't call it trigonal now because we haven't got the top of that triangle. We say that they've arranged themselves in a V shape. I mean, it's upside down if you're thinking about the letter V here, but it doesn't matter, we could rotate it. Now the angle is not 120 because if you remember, a lone pair repels and reduces the angle by 2.5 degrees. So we want to do 120 minus 2.5 equals 117.5. So we are 120 originally, but the lone pair repels more and we get to 117.5. So there are 3 pairs of electrons around the central atom, 2 are bonds and 1 is a lone pair. Electron pairs repel to get as far apart as possible. But lone pairs repel more than bond pairs. The bond angle is reduced from 120 degrees for 3 bond pairs by the having 1 lone pair to 117.5. So we've got this is for 3 pairs, but this is 1 lone pair. Okay, so let's move on and have a look at shapes that have 4 pairs of electrons around the central atom. So we're going to start with methane. So carbon is in group 4. There are 4 hydrogens attached, 4 bonds formed. There's no charge on methane. 4 add 4 is 8. 8 is 4 pairs. So there are 4 pairs and 4 atoms attached. So 4 bond pairs and no lone pairs. So when there are 4 bond pairs and no lone pairs, all 4 bonds repel equally, and now what happens is the shape has to go into 3 dimensions in order to spread them out as far apart as possible. And they're going to take up the corners of a tetrahedron, and so the shape is called tetrahedral. We have to put the C in the middle and we have to draw a tetrahedral shape, which is like a point at the top and then a triangular base pyramid at the bottom. So these 2 bonds are going to be in the plane of the paper, and then we're going to have a wedge coming out to the bottom front corner of the pyramid and a dashed line going backwards and down to the bottom back corner of the pyramid. Now remember, all these bonds are coming down, so all these bonds are coming down towards the floor of a pyramid, and only this one at the top is going up. So 3 down, 1 up. This shape is completely symmetrical. If I rotated it, I'd make a new pyramid with the top one maybe rotating down to the bottom. It'd be the base of the pyramid. It's a tetrahedron shape. Now the angle in this is hard to visualize, but if you look at it, a model of this, you can see that if you spread them out equally, and you can do a little bit of maths on this to work this out, but the angle is 109.5 between any 2 bonds. So this angle here is 109.5. This angle here is 109.5. This angle here is 109.5. And this angle here is 109.5. They're all the same, and even though the diagram doesn't quite look it, they are all the same. Right, NH3 then is another example with 4 pairs, because we've got nitrogen in group 5, 3 hydrogens attached, no charge, that's 8 electrons or 4 pairs. But there are only 3 hydrogens attached, so 3 bond pairs. So to make 4 pairs in total, there must be 1 lone pair. What we do is we take the shape that we just had, which remember went like this, 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 and this. It had a C in the middle before. But there are only 3 bonds, so what we do is we remove this top one and we make it a lone pair. So we've got 3 bond pairs and 1 lone pair. So now instead of being a tetrahedron, it's a pyramid. So it's pyramidal. And instead of being 109.5, remember we're going to do 109.5 minus 2.5 equals 107 degrees. Because the lone pair repels more than the bond pairs. Our next example, we've got oxygen in the middle, because that's the one there's only 1 of, with 2 hydrogens attached and no charge. That's 8 electrons or 4 pairs, but only 2 hydrogens attached. So it must be 2 bond pairs and 2 lone pairs. So again, we're going to take that shape that was like this, and we're going to remove 2 to make them lone pairs. So I like to remove these 2, might as well keep the 2 that are in the plane. We don't need a wedge and a dash. And if you remove those 2 and you put the lone pairs on, you can see you've got this shape. Now, if I were to take that and I were to rotate it, I'm just going to redraw it. You could see why it's called the name of the shape it's called. So I could rotate it so that the 2 bonds are like this, and that is why it gets its name. It's given the name V-shaped. Don't confuse it with the other V-shaped though. It's going to have a different angle. I often, when I'm drawing water, draw it this way up. And the reason I draw it this way up is because when I put the orbitals with the electrons in, it kind of looks like Mickey Mouse's ears, and I just like it that way up. How do I get the angle for this? Well, 4 pairs is 109.5, and we're going to minus 2 lots of 2.5. And if we do that, we're going to get 104.5. So the bond angle here, and the only 2 bonds are here and here, so that's the angle between these 2 bonds, is 104.5. We move on to 5 pairs of electrons. So phosphorus is in group 5, 5 things attached, no charge, 10 electrons, 5 pairs. 5 things attached and no lone pairs. This takes a shape where we have, imagine phosphorus being your waist. You've got your head and your toes, straight up and straight down, and then around the middle we've got a triangular shape. So in the equatorial plane, like horizontally sticking out, we've got a triangle. It's like a hula hoop, but it's a triangle around the centre. And this is called trigonal for the triangle in the centre, bipyramidal because we've got a pyramid on the top and a pyramid underneath. And we've actually got 2 bond angles. You can probably see there's a 90 degrees between the axial, the top and the bottom ones, and the equatorial, the vertical ones and the horizontal ones. But then around the centre, the triangular bit has got a 120 degree bond angle. So we've got 2 bond angles, 90 and 120. So next one, I, group 7, 3 Cls, no charge, 10 electrons, 5 pairs, but only 3 Cls, 3 bond pairs and 2 lone pairs. Now 3 bond pairs and 2 lone pairs can take up 2 different shapes depending on how you want to think about it. Both will be marked right in an A-level exam. Now the lone pairs are going to try to repel each other more. So one lone pair repels another lone pair more than a lone pair repels a bond pair, but that's more than a bond pair repels a bond pair. So there's two different types of shape that they will let you have. You could put the eye in the middle, remembering that we're based off this shape up here. So this was the shape we were going for. Yeah. And if we take this shape and we remove two lone pairs, if we remove this lone pair and this lone pair, this bond, sorry, and this bond, and put them as lone pairs, we end up with this shape. This shape is then trigonal planar. And the angle is actually still 120 degrees because the lone pair on the top would push down 2.5, the lone pair underneath would push back up 2.5. So those kind of cancel each other out. Okay, now the other shape that you can see for this molecule is if you take the iodine again and you draw those bonds on, you get these wedges and dashes. What we find is that if we were to keep the CLs here and here and here, the CLs are 90 degrees apart, and bond pair is the minimum repulsion. It still repels to get as far apart as possible, but it's the minimum. These two, if these two become lone pairs, we've got a lone pair repulsion of 120 and two 90-degree repulsions. But that is actually going to reduce the repulsions more than the shape on the right. This then is called T-shaped. And the bond angles stay 90 degrees because these repulsions are actually in the horizontal plane, and all they can do is affect the one in the horizontal plane. So we actually end up with a 90-degree bond angle. Both of these answers would be marked right in the exam. Both diagrams are right. You're just showing that you understand that you're replacing two of the bonds from a 5-bonded pair shape for lone pairs and the effect that has on the angle. Let's have a go at this last one of the 5 pair shapes. We've got I in the middle at 7. We've got 2 CLs and a -1 charge. So we add 1 on because a -1 means 1 extra electron. 7, 8, 9, 10 total electrons, or 5 pairs. We are on this 5 pairs section. So we've got 2 bond pairs and 3 lone pairs this time because we've only got 2 bonds formed. Now, if we've got 2 bond pairs and 3 lone pairs, and we think about the iodine in the middle, we would have had this shape for 5 pairs. So we're based off the 5 pair shape, but 3 of them are lone pairs. The biggest repulsion is around the middle where they're 120 degrees apart. So we go 1, 2, 3. We put the CLs at the top and the bottom. And because those lone pairs are all in that horizontal equatorial plane, they don't actually affect the bond angle between the two CLs, which are now 180 degrees away from each other. This whole thing is a minus ion. We can see that when we're like this, we're linear. Our last pairs of electrons around our central atom is 6. So we're going to go for sulfur in group 6 with 6 Fs attached, no charge, 12 electrons or 6 pairs, 6 bond pairs and no lone pairs. And when we do that, we're going to take up the shape that minimises repulsion, and that is the shape of an octahedron, which is, although it has 8 faces, has 6 vertices, and that's our 6 Fs. Has 8 faces. It's like a square-based pyramid on top of a square-based pyramid, but it's called octahedron because the name octahedron is the name of a shape. We can see that the bond angle everywhere here is 90 degrees because we've got this square around the middle and then a top and a bottom. And our last one of these, we've got xenon, is in group 8. It's got 4 Fs around it, no charge, 12 electrons or 6 pairs, but 4 Fs. So of the 6 pairs, 4 are bonds, 2 are lone pairs. Again, if we think about that 6 pair shape, it looks like this. We're going to replace the top and the bottom to minimise the repulsion with lone pairs and put the Fs around the side. And we're going to call that a square. That is flat in that horizontal plane and with a 90-degree bond angle. In the next video, we're going to look at some additional types of shapes. So shapes where we've got double bonds, shapes where we've got coordinate bonds, and we're going to look at those separately. So take some time to go through each of these, try to learn the names of the shapes and the angles and the reasoning for why. We only wrote down our explanation a couple of times at the start, but make sure that you're happy saying the explanation.